sample problems. So the first problem that we're going to look at, so suppose that the typical time spent exercising per day for all OSU students comes from a normal distribution with a mean of 28 minutes and a standard deviation of 19 minutes. So we want to know, according to the central limit theorem, what is the distribution of the sample means from a sample size of 150 students? So right off the bat, there are a few things we can answer here. So X is just the number of minutes of daily exercise. The mean for all of them was the 28 minutes right here. So for all OSU students, although I don't know where they would have gotten this information. Sigma, so the standard deviation for that population, they reported as 19 minutes. And the sample size, so this is the one thing that's not of the population, is they took 150 students. So that comes from here. So here, n is equal to 150. Will the central limit theorem kick in? Yes, any time that we have a sample size over 30, we can pretty much regularly say, yes, it's going to be big enough. So central limit theorem will kick in. So we know that it's going to be normally shaped. And not only that, we can say, okay, well, the mean or center of it, the normal distribution will be this, and the standard deviation will be that. So to calculate, so mu of x bar, that's just equal to the mean of the population, which we already have. So that's that 28 minutes. This slightly trickier one, so this sigma of x bar, so that's just sigma of x over the square root of the sample size. So that's going to be 19 minutes divided by the square root of 150. So here, because I cannot do this math in my head, I get something like 1.55 minutes. So the sampling distribution of x bar is going to be normally shaped. It's going to be centered at 28 minutes, and it's going to have a standard deviation of 1.55 minutes. I'm just going to write minutes down here. So that would be the distribution based on the central limit theorem kicking in. Things to note, if we had a sample size that was too small for it to kick in, we just wouldn't know what the shape was. It's not that it has a different shape that we know of. We either can say it's normal, or the central limit theorem kicks in and we can't. So for here, so suppose that the typical time spent exercising per day for all OSU students, so all is the giveaway, that's my population, comes from a normal distribution. And it has that mean and standard deviation. So based on this example, how big do we need our sample size to be in order for the sampling distribution of x bar to be approximately normal? So the big thing to consider is the population comes from a normal distribution. So here, as pretty much as long as you take a sample of at least one, which granted you should take samples bigger than one, trust me, it would be problematic, you'll be good. Your sampling distribution of x bar will be roughly normally distributed thanks to the central limit theorem. 12 and 30, they'd be nice, but it's not necessary that you have a sample that large. Which I think in that last problem we took 150, so we were doing really well. So here we have a pool cleaning example. So we have a company, they record how long it takes their workers to clean a pool, and they do this for all of their customers. So the distribution is strongly skewed. So looking here, not only is it skewed, see this long tail to the right? This is right skewed. So it's strongly skewed with a mean of 1 hour and a standard deviation of 1 hour. And so suppose they go ahead, they take a random sample of 50 of the pool cleaning times, and the mean in their sample is 0.9 hours. So this right here I have so I can fill out what I know about the distribution and then draw the distribution. You might have noticed I kind of stuck just the bell shape in there, and I'm going to fill in. It's pretty much we want to know what numbers or values go here. That's what we'll want. Okay, so right off the bat, I'm just going to say, okay, X is just time to clean the pool. That's the random variable I'm collecting. The average for all of the times to clean the pool, that was just 1 hour. The standard deviation for all those times, that was just 1 hour. And then my sample size is 50. Note the sample mean, that would be X bar is equal to 0.9 hours. I'm not going to use it to answer this question, so I left it out there. So looking here, I have my sample size is 50. Will the central limit theorem kick in? Yes, it should. My sample size is larger than 30. That should be good. Even though this is really skewed, since it's skewed, you'll want a sample of at least 30. 50 is going to be big enough. So this means that we know that the sampling distribution is going to be normally shaped. So now we want to figure out, okay, well, what's the mean and standard deviation? So the mean, so mu of X bar, that's just equal to the mean of the population, which we know, that's 1 hour. Then the standard deviation of X bar, so that's going to be the standard deviation of the population divided by the square root of the sample size. So this will be 1 over the square root of 50. I'm going to round here. It's about 0.14. I'm rounding a little bit. So what do I know? The sampling distribution of X bar is normally distributed with a mean of 1 and a standard deviation of, I'm going to put 0.14. And this is ours as well. So if I want to fill this out, I'm going to go ahead, I'm going to sketch my normal distribution. The mean is the first thing I always label. It's by far the easiest thing for me to put the mean first. So 1 hour goes in the middle, and then each tick mark should be 0.14 away. So 1.14, 1.28, 1.44, nope, 42, I'm not as quick with subtraction, 0.72, 0.58. Okay, and then I'm just going to write hours here. So when I say draw the distribution, we want something that's roughly bell-shaped. 1 should be in the middle, and then I should have 3 standard deviations to either side labeled. And a lot of times you'll see in the assignments, it'll say plus or minus 1, plus or minus 2, plus or minus 3. All it's saying is label all of these tick marks. That's all we want. So now that we have the distribution here of X bar, so it's right here, it's normal with a mean of 1, standard deviation of 0.14. Now we want to actually incorporate. So we have a sample mean that we observed because we took 50 pool cleaning times, and that sample mean was 0.9 hours. So calculate the probability that if I were to take a random sample of 50, I'd get a sample mean of 0.9 hours or less from a sample of 50. So what we're asking is probability that sample mean is less than, well, or equal to is pretty much the same now, 0.9. So what we're going to do, so 0.9, it's somewhere right here, 0.9, and we want probability that's less than. So I'm looking for that area. But since I don't have a normal table for a normal 1.14 distribution, I'm going to translate this. I'm going to calculate a z-score so I can use a z-table to help me find the probability. So my z is going to be x bar minus u of x bar over sigma of x bar. So it's going to be just 0.9 is what I observed in the sample, what we're questioning here, minus 1 is the mean, and then this is that 0.14. And then I plugged it in without rounding on the bottom there. And I get something like, I round to 2 places for a z-score. For a z-score, they should always go out to at least 2 places because the z-table uses 2 places past the decimal. So I get a, first off, this is lower than the mean. 0.9 is lower than the mean of 1. So I should get a negative z-score. So negative 0.71. So this is my z-score. So if I want to find the probability that x bar is less than or equal to 0.9, it's the same as the probability that z is less than or equal to negative 0.71. So here, negative 0.71. The shaded areas on these two distributions are identical. And I can use a z-table to find the shaded area on this one. So, probability is less than or equal to negative 0.71. We're going to need the negative z-table, so negative 0.71. And the z-table does give us the lower than probability by default. So I'm going to split this up. So I can split it up. Remember, I just break it up here. So negative 0.7 and 0.01. Because if I combine them back, I'd get back to negative 0.71. So this tells me which row to use. So the negative 0.7, then column 01. So it's going to be 0.2389. So times when I'm taking a sample of, I'm on the wrong page. So, okay, when I am taking a sample of 50, the probability that when I take that sample of 50, I get a sample mean of less than 0.9 hours, that's going to be equal to the probability that z is less than negative 0.71, which is just 23.89%. So here now they're talking about the central limit theorem and this distribution. So still the pool cleaning distribution. They're asking how big of a sample size should we take in order for our sampling distribution to be perfectly normal. So they're saying for the central limit theorem to kick in. So looking here, if it's normal, n greater than or equal to 1 would be good. But this is not normally shaped. It's not symmetric at all. If n are greater than or equal to 12, if this is roughly symmetric, So look here, it's not symmetric. I can't fold it in half and it's even on both sides. Not even close. So I'm going to say no. I'm going to need a sample size of at least 30 because this is very skewed. So when we have a skewed population, we need a bigger sample size. So now we have a problem. It's a buzzer on a board game. It makes me think of the game Perfection back in the day. And so this board game, you set the buzzer and it goes off anytime between 20 and 120 seconds. Just randomly it's in there. And then we have a population of all buzzer times. They have an average of 70 seconds and standard deviation of 29 seconds. So this is all buzzer times. This gives away, it is a population. So 70 seconds here and then 29 seconds here. Suppose you play a game and you use the buzzer 15 times. So that's getting at n. Consider these as a random sample. So we're treating it as a random sample. They represent the population there. So where the sample mean is a random variable. So we want to know a couple of things. First off, is the central limit theorem going to kick in? So my sample size is 15. So considering this, it's really important that our population isn't skewed. If our population is skewed, this won't work. So here's our population. I would argue this is symmetric. Oops, I can spell symmetric. Right, so because this is symmetric, I would say, hey, you need a sample size of at least 12. This is going to be good enough. So we know that it's going to be normally shaped. So now that we need know it's normally shaped, we need to know, okay, well, the mean is just going to be the mean of the population. So that's 70 seconds. The standard deviation for x bar, that's going to be the standard deviation of the population or the square root of the sample size. So 29 over the square root of 15. This is not doing your head math, at least not for me. I'm with some rounding, I get something like 7.49 in seconds. So I know that putting all this together, x bar is going to be a normal distribution. It's going to be centered at 70. And it's going to have a standard deviation of 7.49. And I'm just going to write seconds down here. So now if I want to fill it out, always start with the mean, the middle. It's going to make life a lot easier. So might even write these at an angle. So 70 and then add 7.49. So 77.49. Oops. Add again. 84.98. Then 92 point, I don't know, something 7. Four 7. And this is 62.51. 55.02, 47.03. So this would be defining the distribution. It's telling us it's normal, where it's centered, and its standard deviation. And this would be drawing it. So we want the mean and we want 3 standard deviations to either side. So now we're going to focus on that sample of 15. What did we actually see in that sample? Okay, so we're still using this example where we're looking at the buzzer times from this game. And suppose I want to play a game and I use the buzzer 15 times. And when I do, I get a sample mean of 80 seconds. So 80 seconds for these 15 buzzer times. So looking here, this is from that last slide, but prettier, right? So 80 seconds, it's somewhere between 1 and 2 standard deviations away from above the mean. So calculate the probability that you take a sample of 15 buzzer times and you get a sample mean of 80 seconds or more. So I want this area up here. So I want to know, what's the probability I randomly select 15 and get an average higher than that? So here, I have my mean for my sampling distribution. I have the standard deviation for my sampling distribution. I'm ready to go ahead and calculate. I can calculate a z-score and then use a z-table to find the probability I want. So if I get z is equal to, so x bar minus u of x bar over sigma of x bar. So 80 is what I observed, minus the mean there is 70 over standard deviation here, 7.49. You get 10 over something, so it's going to be between 1 and 2. I'm going to get positive 1.34. And I only round out to 2 places past the decimal because with z-scores, it doesn't really make sense using a table that goes to 2 places, going further than out than 2. Okay, so probability that x bar is greater than, if you go to 80 seconds, that's going to be the same as the probability that z is greater than or equal to positive 1.34. So 1.34. The shaded areas are equal to each other, but I have a table for the normal 0, 1. That's why we converted over to z. So finding the probability here, there are going to be a couple of steps. So positive 1.34. I'm going to break it up. So positive 1.3, then 0.04. Line them up. So 1.3 is my row, 0.04 is my column. I get this 0.9099. So this is the probability that z is less than. So you have to stop and consider, do I want the probability less than, or do you want higher? Because if you want higher, it's 1 minus 0.9099. So probability will fill, probability that z is higher than positive 1.34, that's going to be 1 minus 0.9099, which is 0.0901. So this would happen about 9% of the time you take a random sample of 80 buzzer times, so this would happen that about 9% of the time that if you take 15 buzzer times and get an average of 80 seconds or longer. So here, probability, just putting it all together, probability x bar is greater than or equal to 80 is going to be the same as probability that z is greater than or equal to 1.34, which is 1 minus 0.99. Oops. 0.99.0901. So looking at this problem, suppose that we had a different sample size. So instead of taking 15 buzzer times, we're going to take 30 buzzer times. So we want to figure out, okay, well, if we did that, what changes for our sampling distribution of X bar? So if we change our sample size from 15 to 30, then, so the first one, the sampling distribution will look more like the population. The sampling distribution will have a smaller standard deviation. We'll have a larger standard deviation. So things to note is my standard deviation here, sigma of X bar, that's sigma of X over the square root of N. So it is going to change if my sample size changes, right? If I make my sample size bigger, this value is going to change. So I would argue it's going to be one of these two. Honestly, the bigger your sample size gets, the more you can guarantee that your sampling distribution will be normally shaped. So it's not going to be A. So here, this was what, 29. If I change it to 30 over the square root of 30, I get something like 5.29 seconds. So this is smaller. It became smaller, right? So it was less than that 7.49 seconds when we had a sample size of 15. So making our sample size larger makes the standard deviation smaller. Basically, the sample mean fluctuates less from sample to sample if you take a bigger sample. So that's it for lesson 21, and we're going to start getting into estimation. So what that means, confidence intervals.